In this lab, we will explore the physical properties of metals. As always, before beginning any experiment in the laboratory, be sure you are familiar with laboratory safety requirements. For a demonstration of basic lab safety rules, you can watch our video entitled Lab Safety. The physical properties of metals vary greatly from one metal to another, so there is no single physical definition that applies to all metals. Instead, metals are defined by their chemical properties and by their position on the periodic table. Metals are one of three classes of elements on the periodic table. They occupy the left side and center of the periodic table. The lanthanoids and actinoids at the bottom of the periodic table are also metals. The second class are the nonmetals. Most of the nonmetals occupy the right side of the periodic table. The one exception is hydrogen, which appears at the top of group 1 on the left side of the table. Members of the third class, metalloids, are located between metals and nonmetals. They occupy parts of groups 13, 14, 15, and 16. In this lab, we will focus on metals. When we think about metals, the first thing that usually comes to mind are substances that are shiny, like gold and silver, or substances that are strong and hard, like iron and titanium, or substances that are dense, like bronze and lead. While many metals are shiny, hard, and dense, others are not. This piece of sodium does not look shiny. It looks more like a dull gray rock than a shiny metal. Not only is sodium not shiny, it is not hard either. In fact, it is so soft it can be cut with a knife. Sodium is less dense than water. If we drop a small piece of sodium into a beaker of water, it will float on the surface of the water. Even though sodium may not fit our idea of a metal, it is classified as a metal. Some physical properties we usually associate with metals are luster, conductivity, malleability, ductility, a high melting point, high density, and hardness. Only a few metals possess all of these physical qualities, but all metals have at least some of them. If you polish the surface of an object made of silver, it shines with a mirror-like quality. The light-reflecting quality of a substance is called luster. Some metals, such as chromium and gold, maintain a high luster. But most metals corrode when they are exposed to gases in the air. When a metal corrodes, its luster is hidden beneath a layer of tarnish. This sample of sodium does not appear to have luster because it is coated with a sodium oxide tarnish. When we cut open the lump of sodium, we expose the shiny metal inside. The shiny luster is visible for a short while until it corrodes again and turns gray. Metals also possess conductivity. Conductivity is the ability of a substance to conduct heat or electricity. Metals conduct heat, which is why metal pans are used for cooking. Metals also conduct electricity. We can test the electrical conductivity of metals with this continuity tester. The tester produces an electric charge. If we touch the lead to one end of this copper strip and then touch the end of the probe to the opposite end, the light comes on because an electric current is being conducted through the strip. As we can see, copper is an excellent conductor of electricity. Iron is also an excellent conductor. So is zinc. Let's try the same procedure with sodium. As you can see, sodium also conducts electricity. So even though sodium does not have the physical properties of some other metals, it does possess conductivity. Most metals also possess malleability and ductility. Malleability is the ability of a substance to have its shape changed without breaking or cracking. Many metals, such as iron and steel, are malleable, so they can be pounded into different shapes without breaking. A blacksmith uses this property to bend steel to make tools or horseshoes. Ductility is the ability of a substance to be stretched without breaking. Copper is so ductile that a copper rod can be stretched out and pulled into thin wire, and then rolled onto reels for use in electric wires, motors, and magnets. Most metals also have a high melting point. Steel, which is an alloy of iron, must be heated to higher than 1,400 degrees Celsius before it melts. Since tungsten can withstand temperatures over 3,000 degrees without melting, it is used for filaments in incandescent bulbs. However, some metals have a much lower melting point. Alloys of metals such as tin, bismuth, cadmium, and lead are used to solder electrical connections because they melt at 400 degrees or lower. The solder is melted onto an electrical connection on a circuit board, where a wire must be connected. When the metal solidifies, the wire is permanently connected to the circuit board. 3 metals, gallium, cesium, and francium, will melt at less than 30 degrees Celsius, which is just slightly above room temperature. Gallium melts at 29.8 degrees, so it will melt if you hold it. However, you should never try this with cesium or francium. Cesium is so reactive that holding it in your hand might cause an explosion, and francium is highly radioactive. Mercury may be the most unusual metal. Mercury has luster, and it has conductivity, but it is a liquid at room temperature. So, mercury is obviously not malleable or ductile, and it has a low melting point of negative 38.8 degrees Celsius. However, mercury possesses one other physical property shared by many metals. It has a high density. Density is the amount of mass in a substance per unit of volume. 1 milliliter of water is the same as 1 cubic centimeter. 1 cubic centimeter of water has a mass of 1 gram, so water has a density of 1 gram per cubic centimeter. Most metals are much denser than water. If you drop a piece of lead into water, it will sink because lead is denser than water. However, some metals have very low densities. Sodium has a density of 0.97 grams per cubic centimeter, which is less dense than water. So, if you drop a piece of sodium into water, the metal floats. The densities of potassium and lithium are even less than sodium. Potassium has a density of 0.89 grams per cubic centimeter, and lithium has a density of 0.53 grams per cubic centimeter, which is about half the density of water. Some metals have much higher densities. For example, iron has a density of 7.9 grams per cubic centimeter. Lead has a density of 11.3 grams per cubic centimeter, and mercury has a density of 13.5 grams per cubic centimeter. Osmium, with a density of 22.6 grams per cubic centimeter, is twice the density of lead. The last physical property of metals we will discuss is hardness. Hardness is defined as the resistance of a solid substance to being scratched or deformed. Metallurgists use a hardness testing machine to determine the hardness of a metal. The machine rates the metal's hardness by the amount of pressure needed to put a dent in the metal. Since we do not have access to a hardness testing machine, we will use a scratch test to determine the approximate hardness of some metals. A scratch test is based on the Mohs hardness scale that was devised by German geologist Friedrich Mohs in 1812. The Mohs hardness scale compares the hardness of substances to the hardness of 10 reference minerals. If a reference mineral leaves a scratch on the surface of a test metal, we know the reference mineral is as hard or harder than the test metal. If the reference mineral does not leave a scratch on the test metal, we know it is softer than the test metal. By comparing the hardness of a metal with the hardness of the reference minerals, we can determine the approximate hardness of a metal. The hardest reference mineral on the Mohs hardness scale is diamond, which has a hardness value of 10. Currently, no naturally occurring substance is harder than diamond, but there are some synthetic materials that have a higher hardness value. The softest mineral on the Mohs hardness scale is talc. Talc, which is a form of magnesium silicate, has a hardness value of 1. Talc is so soft that we can scratch it with a wooden toothpick. Glass has a hardness value of 5.5, which is about halfway between talc and diamond. For this reason, a glass plate is often used as a general reference for hardness. If the unknown substance scratches the glass, we know it has a Mohs hardness value of 5.5 or greater. If the substance does not scratch the glass, we know it has a Mohs hardness value of less than 5.5. This will help us determine which reference minerals to use when performing the scratch test. Metals have a wide range of hardness values. In fact, 5 metals are even softer than talc. The softest metal is cesium, which has a hardness value of only 0.2. Cesium is so soft you could scratch it with your fingernail. But since cesium is extremely reactive, this sample is sealed in a glass ampule. The metals rubidium, potassium, sodium, and lithium also have hardness values of less than 1. To conduct a hardness test on sodium, we first try to scratch the glass plate with a piece of sodium. As expected, the sodium does not scratch the glass plate, although it does leave a smear of oil on the plate. Since sodium is softer than talc, we should be able to scratch its surface with a piece of talc. We see a definite scratch in the sodium, so we know sodium is softer than talc. Since there is no reference mineral with a hardness less than 1, this scratch test does not tell us the exact hardness of sodium, but it does tell us that the hardness value of sodium is less than 1. This is consistent with what we already know about the hardness of sodium, which is 0.5 on the Mohs hardness scale. Next, we will test the hardness of tin. We will first try to scratch the glass plate with a piece of tin. Tin does not scratch the glass plate, so we can assume the hardness value of tin is less than 5.5. Next, we try to scratch the tin with a piece of talc. The talc does not scratch the tin, but it does leave a streak, so we brush away any mineral residue to confirm it is a streak and not a scratch. Since talc does not scratch the tin, we will test the tin with the next reference mineral, which is gypsum. Gypsum is a hydrate of calcium sulfate, and it has a hardness value of 2. Let's see what happens when we try to scratch tin with gypsum. We need to brush away the residue to see the scratch. Talc does not scratch tin, but gypsum does. So we know the hardness value of tin is greater than 1, but less than or equal to 2. Since the actual hardness of tin is 1.5, this is consistent with our experiment. Next, we will test the hardness of copper. To test the hardness of copper on the glass plate, we use a copper-coated penny. Since the penny does not scratch the glass plate, we can assume that copper has a hardness value of less than 5.5. When we try to scratch the copper strip with talc and gypsum, both minerals leave streaks on the copper, but neither mineral scratches it. Since neither mineral scratches the copper strip, we will try the next reference mineral, which is calcite. Calcite is a form of calcium carbonate, and it has a hardness value of 3. Because gypsum does not scratch the copper strip, but calcite does, we know the hardness value of copper to be more than 2 and less than or equal to 3. Since copper has a hardness value of 3, this is consistent with our experiment. The next metal we will test is cobalt. We try to scratch the glass plate with a piece of cobalt. Cobalt does not scratch the glass plate, so we can assume that cobalt has a hardness of less than 5.5. To save time, we have already performed the scratch tests with talc, gypsum, and calcite. Since none of our reference minerals scratched the cobalt, we will try the next reference mineral, which is fluorite. Fluorite is a form of calcium fluoride, and it has a hardness value of 4. Let's try a scratch test with fluorite. Fluorite does not scratch cobalt, so cobalt must have a hardness value of greater than 4. The next reference mineral we will try is apatite. Apatite is a form of calcium phosphate, and its hardness is 5. Fluorite does not scratch the cobalt, but apatite does. From this, we know that the hardness value of cobalt is more than 4, but less than or equal to 5. The actual hardness value of cobalt is 5, so the experiment is consistent with our test results. Our next test metal is vanadium. Vanadium easily scratches the glass plate. Since vanadium scratches the glass plate, we know it has a hardness value of 5.5 or greater, so we do not need to scratch test it with talc, gypsum, calcite, fluorite, and apatite. We will try the next reference mineral, which is orthoclase. Orthoclase is a form of potassium aluminium silicate, and its hardness value is 6. Let's see if orthoclase will scratch this piece of vanadium. The orthoclase does not scratch the vanadium, so we can assume that the hardness value of vanadium must be greater than 6. The next reference mineral we will test is quartz. Quartz is a crystal form of silicon dioxide, and it has a hardness value of 7. Let's see if quartz will scratch vanadium. Since orthoclase does not scratch the vanadium, but quartz does, we know that vanadium has a hardness value of greater than 6, but less than or equal to 7. Vanadium has a hardness value of 7, so this is consistent with our test results. For our last scratch test, we will use chromium. Chromium easily scratches the glass plate. Since chromium scratches the glass plate, we can skip the tests with talc, gypsum, calcite, fluorite, and apatite. Let's see if orthoclase will scratch chromium. Since orthoclase does not scratch chromium, we will try the next reference mineral, which is topaz. Topaz is a complex form of aluminium silicate and fluorine, and it has a hardness value of 8. Let's see if topaz will scratch chromium. Topaz does not scratch chromium, so we can assume that the hardness value of chromium is greater than 8. We can move on to the next reference mineral, which is corundum. Corundum is a form of aluminium oxide, and its hardness value is 9. Let's see if corundum will scratch chromium. Since topaz does not scratch chromium, but corundum does, we can assume that the hardness value of chromium is more than 8, but less than or equal to 9. Since the actual hardness value of chromium is 8.5, this experiment is consistent with our test results. Chromium is the hardest metal, so we do not need to perform any more scratch tests. In our next lab, we will discuss the chemical properties of metals. At this time, proceed with the corresponding activities.